So our next presenter is Sébastien Piechurski. He's been working on Lustre since 2005, after spending 10 years at level 3 system support engineer at Pilatos. He's now a storage and I/O performance advisor, performing I/O benchmarks and architecture for pre-sale.
So hey everyone. Today I'm here to present you a work about Lustre in an LNet rooted environment. This talk was inspired by an installation which was performed at ECMWF the last year, and so I would like to give a bit of context before going into the technical details. So ECMWF is the European Center for Medium-Range Weather Forecast. So as its name implies, they are doing forecasting, and for this they rely on a lot of input data and parameters, as you can see, which are collected about all that happens on land, ocean, atmosphere, and things like that. That means that they need to process a lot of data, and for this they need a large computation facility. So for this we provided them last year in their brand new center in Bologna, Italy, some clusters based on our Sequana XH2000. So you can see the center here. The facility is composed mainly of 2 data halls, so that you can see here. I don't know if we, okay. And so those are actually divided into what are called 4 complexes, where each complex is actually including 2 clusters. So one cluster is based on the XH2000, where the nodes are grouped in cells of 4 racks. So there are 5 cells per cluster, and this means there are about 2,000 nodes per cluster. There are 4 complexes divided across the 2 data halls, and so we get in the end about 8,000 nodes aggregated. On the storage subsystem, everything is based on DDN appliances. There are 10 independent exascalar systems, again, which are divided across both data halls. And so you get 2 types of file systems. One is called time critical, which is for production, day-to-day production. And the other file systems are for research. In the time-critical storage, you have 2 file systems which are 700 terabytes based on flash, and 2 other file systems based on HDD with a 5 petabytes capacity. So all the file systems are accessible from all complexes. Each complex, so as I told, is composed of about 2,000 nodes. You can get different specs here, but the main interesting factor is that we get 2,000 nodes and in total 8,000. This is about the specs of the file systems. So the flash-based file systems are 700 terabytes and able to sustain about 300 gigabytes per second. And the HDD-based are 5 petabytes and able to sustain more than 100 gigabytes per second. Then comes the file systems for the research, which are 13 petabytes and able to sustain 260 gigabytes per second. So here you can see the way the complexes are laid out. So you have the two halls. In each hall, you have 2 complexes, and all complexes will access both data hall storage fabrics through 30 LNet routers each. So you can see that already there is quite a proportion in the number of nodes against the number of routers, which is a part of why I'm giving this talk. So before explaining what kind of troubles we could have seen, I would like to remind a bit of theory about LNet routing. So a part of the information I'm going to give is from source browsing, and some parts are also assumptions. The source was based on the 2.12 version, so some things might be outdated, some others might be incomplete, but I guess a lot of people here could correct me if I made a mistake. So when you have a router, let's take the example that you have one client, one router, and one server. What you need to remember is that the network is just like the over network protocol. It's based on different layers, like the OSI model. And for the top layer, we have the module PTL-RPC, which is handling RPCs, so RPCs for remote procedure calls. Physically, those RPCs are not going directly from a peer to the other. They will first get pushed to the lower layer, which will then handle splitting the data to be transmitted physically. Each layer has its own grain size, so the PTL-RPC is able to send up to 16 megabytes of data per RPC. The LNet layer is able to send up to 1 megabyte. And so in this example, I will talk about InfiniBand, but of course, it is dependent on which network you will use, as you can have the GNI, LND, or TCP LND. And in the case of InfiniBand, the packets are at most 4 kilobytes. In the same manner, each layer also has its own timeouts, or a set of timeouts. The RPC level has the set of adaptive timeouts. You also get the pinger eviter in this. The LNet layer gets the LNet transaction timeout parameter. And you also get, in the case of using routers, the router ping timeout. I will go more in details about this later. And the InfiniBand network itself also has a timeout on the life of packets, which is defined in OpenSM by the subnet timeout parameter. You also have something which defines kind of parallelism in the different layers. So at the RPC level, you will get max RPCs in-flight RPCs to each target on your file system. At the LNet layer, you get credits, which is the global parameter, and then peer credits, which defines number of messages that can be sent between two peers. I didn't look for the IB level, but we don't really need it. So let's take the example that we want to send a 4 megabyte bulk write RPC from a client to a server for which the RPC connection is already established. And we have the LNet router in between. So an LNet router will have statically allocated buffers that can be used to store the data between the client and the server. So at first, the RPC is pushed to the LNet layer, which will handle what are called messages. The RPC in-flight counter will be incremented, so to keep track of the number of RPCs that are sent to the target we are sending to. And the LNet layer will then split this RPC into 1 megabyte messages at most. Once the LNet layer has pushed, begins to send the message, it will send it to the router. There will be an RDMA transaction which will define on which buffer the different data needs to land. And at the LNet layer, you get the peer credits counter, which gets decremented also to keep track of the number of messages which are sent. The LNet layer will then push this to the lower layer on the IB side. And the HCA will itself split the messages into 4 kilobytes messages at most. So the HCA pushes those data 4 kilobytes by 4 kilobytes to the LNet router, which will slowly fill up the different buffers. And each time you get a new message which begins to be sent, you decrement again the peer credits counter. Once you get a buffer which is complete, or one message, I would say, the router is then able to forward it to the Lustre server, and using the same mechanism, it will send it to the Lustre server. So on its side, it will again decrement the peer credits, which is between the router and the server. The same mechanism goes on and on for the different messages until you get one message complete on the server. At this time, the server will acknowledge the reception of the message to the router and continue to receive the other messages. So by acknowledging the reception of the complete message, it also returns the peer credits which was associated to it. So we can increment the peer credits on the router side. The same goes for other messages, and once the LNet router received acknowledgement for a message from the server side, it will then also send the acknowledgement to the client side, which will increment the peer credits again, and then free the buffer which was holding the message. And this goes on and on until we've processed all messages. And on the server side, once we get all messages reconstructed, the LNet layer on the server side will be able to push those to the PTRPC layer to reconstruct an RPC, at which point we get the complete RPC back, which can be then processed. And once it is processed, the Lustre server will send another message using, again, the same mechanism in the other direction to get a reply. And at this time, the client will decrement the RPCs in flight so it can send over RPCs again. So, of course, everything here is oversimplified. There are a lot more mechanisms behind, but I thought it was useful to understand what comes after. Yeah. So, yes, in theory, we have one client, one router, one server, so everything is fine. But in practice, here is what we get. So you get thousands of clients, you get a handful of routers, and a bit more than servers in behind. So in terms of parallelisms, you can get a lot of problems. And this is why we need timeouts and credits, and to adjust those accordingly so that everything is smooth in the system. So in practice, in our first attempt, all clients were able to talk to all routers, all LNet routers, and in this configuration, we got frequent occurrences of the following messages. So you essentially get timeouts on the RDMA level, and then you get other messages, you get client evictions, dirty page discards, IO errors, ultimately on the applications, which obviously is not what we expect. The first analysis of this problem was that as we get all clients being able to use all their credits to each router, if you make the count, that means that you can get up to 1.8 terabytes in transit, which obviously is quite difficult to pass in 50 seconds, which is the default transaction timeout at the LNet level. That would mean you have to reach at least 36 gigabytes per second to have everything go on without timeout. And with HDD-based file system, for example, or if the pattern is not optimal, then it's very difficult to reach this. So the first mitigation that we put in place was to reduce this by assigning 6 routers at most for each client. So we did this by saying, okay, we have 5 islets per cluster. So each islet is 384 clients. And we dedicate 6 routers to those set of clients. That means that we reduced by 5 the quantity of data that can be in transit at any one time. And it means we reduce the performance that we need to reach to get everything passed in the 50 seconds window. So everything seems to be fine at this point, but well. So this is the configuration that we would reach. But actually, this is not good enough. We still get some troubles from time to time, even if it's much better. So we began to play with the different timeouts, but each time we were playing with one parameter, there would be another trouble coming on the other end. So we settled and said, okay, we need to understand what are the dependencies between the different parameters, and so let's think about it. So in the different parameters, we have first the peer credits. So as I said, this is the number of messages that you can send from a peer to another peer. So it was set to 32. I guess it was, this is the value that was already set when we began. I guess we kept it because we thought it would probably lower the single node performance if we would lower it. Then comes the credits parameters. So this is the same, but this is global, which means that you can't go beyond this value, even if you have more peers that you can address. So in the SMWF case, we set this to the number of routers multiplied by the number of, multiplied by the number of storage fabrics, because we have 6 routers for each storage fabric, actually. So this is 12 in total for each client. And multiplied this by the number of peer credits. So that means you can address for up to 384 messages at once for any single client. On the routers, it's a bit different because you need to be able to address all clients and servers at once. So you multiply essentially by the number of facing peers, which in our case is the 384 clients multiplied by 4 because we have 4 complexes. Plus the 138 servers on the other end. So we rounded the value to, let's say, 64K, just because we could. Then comes the number of buffers that you want to allocate. So the buffers, as I said, are at most 1 megabyte. You have different sizes. You have tiny, small, and large. The large is 1 megabyte. The small is actually 1 page. And the tiny is actually only a few bytes, so you don't really bother making them quite large in quantity, I mean. So ideally, you want also to be able to store all the messages which come from all facing peers. So in the case of the routers, these are the number of clients plus the number of servers multiplied by the number of peer credits for each of them. In our case, this means we need to have 64 gigabytes of RAM because with 64,000 of at most 1 megabyte messages, you get 64 gigabytes of RAM. So this is something you need to take into account when you're doing the architecture to size the RAM on the routers. Then comes the timeouts. So as I said, on the lowest layers for IB, you have the subnet timeout, which is by default 18, and so that's actually 4 microseconds to multiplied by 2 to the power of 18, which is about 1 second. And so at some time we found that there was 7 retransmissions after this was dropped, but I didn't find the reference for this presentation. So if any one of you have a reference on this, well, you're welcome to tell it. Then comes the transaction timeout. So this one defines the yes, you have the transaction timeout and the LNet retry count. So these ones both define the timeout and the number of retransmission for a single message. And in the code, you can see that the retransmission happens actually every LNet transaction timeout minus 1 divided by LNet retry count plus 1. So in our case, and you probably want the retransmission to be after the IB lower level timeout. And so as each message transmission is sent on a different router in a round-robin fashion, we decided that we wanted to have a retry, enough retries to, let's say, try different routers in case one router was down, so that we can successfully send the message. So we set 61 and 5, which means we can have 6 attempts and every 10 seconds. Then comes the live router check interval. So this is when this defines when you want to check that a router is still alive, after which the number of seconds you want to wait. The router ping timeout defines how much time you wait once you want to check for the router to decide whether it is still alive or down. And the live router check interval plus the ping timeout needs to be kept below the return, well, a part of the timeout of the LNet. In our case, we wanted it to be to have the opportunity to resend it before an IB packet is dropped. So we set both to 30 and 15. The dead router check interval is the same as live router check interval, except that it is triggered when the router is considered already done. Then comes the adaptive timeout. So I will try to be quick. In short, it means the adaptive timeout works so that the server is able to notify the client a bit before the deadline of an RPC that it needs more time to be processed. So it will send what is called an early reply and saying it that, okay, please extend the timeout by a certain value, which is, in this case, 80 extra. And it will repeat this process until the RPC is either processed or that we reach the 80 max value. And so in our case, we set 80 min to 75 seconds. So we need this to be higher than the LNet transaction timeout, so that the lower layer already timed out before. Then you have the early margin that you want to be high enough so that you can have several retries at the lower layer. Then comes the 80 extra, which we've set to 2 times the early margin so that you don't retry, notify again the clients too often. And then the 80 max is the default of 10 minutes. So that's about it for the talk. So this results in a kind of dependencies of the different parameters between them. So, well, we can discuss it if you want. Just a few credits. I wanted to thank Alexandre Louvet, who supported this work and is always supportive in our team. And also ECMWF team, who allowed me to give concrete examples.
Thank you, Sébastien.
Okay, that's it.
Any questions? Nobody?
So with all those tunings now, if you lose a router, it's quite transparent, or still you have like some file system that hang from the clients?
We can, well, the installation is now quite resilient. However, in the case of routers, if we lose really the router, there are still some few things that we didn't really clarify, but which are not the fact of the different timeouts. So, yeah, we're quite, we are happy with this setup because it changed from one day to the other completely the stability of the file system.
Okay, so and from the application point of view, if you have an issue somewhere, usually like the application crash or just hang and then recover?
Usually, yes.
Yeah.
If there are no other facts like the IB network, which has some other troubles, yeah.